Consider a point charge Q placed in vacuum. This charge Q produces an electric field everywhere its surrounding. The direction of the electric field is radially outward from the positive point charge and points towards a negative point charge. The magnitude of the electric field decreases as distance increases from the point charge. If two unlike charges are placed close to each other, they get attracted. If two like charges are placed close to each other, they get repelled. Here is a positive charge. We can imagine two equal and small elements of area placed at the points A and B, which are normal to the field lines. 4 lines are passing through the area element placed at A. Only 2 lines are passing through the area element placed at B. The number of field lines cutting the area elements is proportional to the magnitude of the field at these points. Since there are more number of field lines at A, electric field at A is stronger than at B. So, the electric field decreases as the square of the distance from a point charge. But the number of field lines crossing a given area remains constant. Let us consider some lines of fishes crossing in through a water column. Place a net there and try to find out the number of fishes crossing in that net. If vector A be the area vector and vector F is the fish intensity crossing area vector A, then the number of fishes crossing across the given area equal to fish intensity dot area. This will give the number of fishes crossing per area. Something crossing per area can be called as flux. So, this can be called as fish flux. Just replace these fish lines by the electric field lines like fish intensity F, here electric field intensity E, then the amount of field lines in a given region equal to electric field dot area vector. That is, electric flux equal to vector E dot vector A. Electric flux is the measure of distribution of electric field through a given surface. That is, the number of field lines that intersect is flux. It is represented by the vector E dot vector A or EA cos theta. In the lower class, you may learn area is a scalar quantity. If you hold the area element normal to the flow, maximum field lines will flow through it than if you hold it with some other orientation. This shows that an area element should be treated as a vector. It has a magnitude and also a direction. How to specify the direction of the planar area? Clearly, normal to the plane specifies the orientation of the plane. Thus, the direction of the planar area vector is along its normal. How to associate a vector to the area of a curved surface? We imagine dividing the surface into a large number of very small area elements. Thus, small area element may be treated as planar and a vector associated with it. Here, these lines are represented by uniform electric field. This rectangle is divided into many small elements. The angle between the area element and the electric field is theta. Then, d pi can be written as vector E dot vector ds. This can be written as EDS cos theta. The total flux will be the integral of d pi. So, flux is a scalar quantity.